right now?
Test, test. Okay, so the last few people are coming in, so it's time to start our afternoon session, which is about observables and quantum gravity, and it is my pleasure to introduce our first speaker today. Also, there will be 2 long talks and 1 slightly shorter talk with brief time for questions, but afterwards there will be a long discussion session, so there's enough chance for you to ask your questions. So I'm happy to introduce our first speaker, Philip Höhn from the Okinawa Institute for Science and Technology, and he's going to tell us about observables and dynamical frames in quantum gravity.
Yeah, thanks very much, and thanks to the organizers for having me here. I want to talk about how the concept of dynamical frames that has seen also a lot of attention in recent years in the context of quantum reference frames, how that can help in the construction and interpretation of observables in gravity, and in particular also how it can help to unify different approaches to gravitational observables. So the talk will be mostly based on this paper already from last year. Some of you might have seen talks by me about that paper. For that reason, I'll try to focus on some aspects that I didn't speak about before. So the talk therefore starts with one of the very basic questions in gravitational theories that all of us will have stumbled upon at some point. The question of what are actually interesting observables in gravitational theories, and how do you construct them in the face of diffeomorphism invariance. And there exist multiple approaches, and they depend a little bit on the community that you come from, and at least broadly speaking, you can separate at least a large class of them into 2 camps. One is the so-called Dressed Observables program that's more for the HAP-TH people. And then most of the not so HAP-TH people often work with relational observables. But this division doesn't stop here. In fact, even the relational observables program has at least 3 different classes. There exist covariant representations of them that also some of you, in fact, actively work on, and we might hear about that also later this week. There exist so-called single integral representations of relational observables. Again, some of you actually work on that, and then there also exist canonical power series representations of relational observables. And with so many approaches, one can, of course, ask what's the relation between them? Is there any one approach that's actually somehow right or better, or maybe even more suitably, does there exist kind of one approach that unifies them all and encompasses them all? And that's a little bit the aim of this talk, to give you such a unifying approach. It has to do with the concept of dynamical reference frames. One disclaimer I should make is, although this is about observables in quantum gravity, I will actually exclusively speak about classical gravitational theories. But in any case, it's worthwhile to understand them a little bit better. And yeah, here, at least with these notions of observables, there's always some relational ideas involved, and the question is whether we can make the relation to dynamical frames more precise in the sense that we can understand them as being descriptions relative to dynamical reference frames. And then we can try and see whether we can also connect it with the notion of dynamical frame covariance, where we can translate between different frame perspectives and maybe even formulate general covariance in the language of dynamical reference frames. Okay, if some of these names here don't mean much to you, I will at least try to give you some taste of what these approaches actually are in this talk. Okay, so gauge invariant observables. So just as a little bit of a setup here, we're going to be interested in observables that are invariant under bulk diffeomorphisms, which are gauge. And so what we want to look at is kind of some objects O defined on field space. So square brackets mean it's a functional of some field configurations, and this phi in the sense of the covariant phase space just labels field configurations, so configurations of all your dynamical fields. So it's not just a scalar field or something like this. And diffeomorphisms act by push forward, and so we're going to look for observables that have that property. And a priori, so sometimes you hear that it's very difficult to find gauge invariant observables in gravity, but at face value, it's not true, because we can always find any old covariant top form that has this property, and then just integrate it over all of space-time, and you'll find that this gives you some gauge invariant observable. And as an example, you can take alpha to be just basically the Ricci scalar, and then you get the Einstein-Hilbert action, which in a strict sense is a gauge invariant observable. But of course, it's not a very informative one a priori. It doesn't tell you very much about local physics. And so the more interesting or relevant question is, how do we actually construct phenomenologically relevant gauge invariant observables that have some local information? And there's, of course, as many of you know, the tension between gauge invariance and locality, or at least in a traditional sense of locality in gravitational theories. And you can see that at the level of a scalar field. So scalar fields will be denoted by var phi as opposed to this here, which is a field configuration. So diffeomorphisms act on that by push forward. So in this way, so that already tells you that the value of the scalar field at some space-time event x can be gauge invariant only if either it's a constant, that field in space-time, or if x is a boundary point where gauge diffeomorphisms might act trivially. Now, clearly we want to have more interesting local observables, and so a priori, okay, there's a tension with the traditional notion of locality in terms of fixed labelings of events. And the question is, how do we go about this? And well, we're clearly not going to give up gauge invariance, so we have to somehow adjust our notion of locality. And this notion of locality that kind of fails here is one based on fixed, so that is non-dynamic reference frames. And so that brings us to the notion of dynamic reference frames. So this is a quote of Einstein that I'm sure many of you have seen before, but it kind of fits here, so let me just quote it. And that's the statement that the theory, so general relativity, introduces two kinds of physical things: measuring rods and clocks, so basically the reference frames, and then all other things like fields and so on. And this, in a certain sense, is inconsistent. Strictly speaking, measuring rods and clocks would have to be represented as solutions of the basic equations. And so that's kind of what we're trying to head at, a realization of this, or a resolution of this. To get a bit of inspiration, let's quickly look at special relativity with internal frames, so tetrads. Really, what are they? These are maps, at least if I apply them to vectors, so kind of a map from Minkowski space to some other space. Well, they're actually group valued in the Lorentz group because of normalization conditions. And here you can act on these frames by gauge transformations, which would be just basically space-time Lorentz transformations. And then you can use these tetrad vectors to contract whatever other vector you might be interested in to turn it into something that's invariant under space-time Lorentz transformations. Now, in gravity, we're going to do something very similar, but here we're going to look at something dynamical, and these will be maps that will take us from space-time to some other space we can call frame orientation space. And they can also be, they need not be, but they can be group valued if it happens that this map is something like a diffeomorphism. And so they will depend on the field configuration, and so in particular on the solution in the end. And so in that sense, they will define as something like a dynamical coordinate system. And similarly to these gauge transformations here for, in quotation marks, for tetrads, what we want to look at is frames that transform kind of nicely or gauge covariantly under gauge transformations. And so we require that they have this property here. Now, when you put coordinates on O, this is just tantamount to meaning, so they transform basically as scalars. So when you put coordinates on the space O, then what they give rise to is nothing else than some dynamical space-time scalars that are somehow constructed out of the field content of your theory. Okay. Now the question is, how do we actually realize that? And let me discuss this now in the context of dressed observables, so this kind of HepTH program. And here the aim is typically that we're given some naked or bare quantity that's not invariant by itself, and somehow we want to dress it with some other degrees of freedom into some composite operator that is gauge invariant. And for scalar fields, so let me just illustrate this on scalar fields. This means in practice nothing else than finding a dynamical specification of space-time events. So they depend now on the field configuration in such a way that under gauge transformations, this transforms like so. Now, why do you want to have this? This basically means that if you evaluate a scalar field at such a dynamically defined event, it will be gauge invariant. And just to give you a bit of an intuition, so in particular in the HapTH community, so a lot of people like boundaries, so they like to use the boundary as a reference, and so often the stressing means kind of anchoring your description relative to a boundary. A very simple example of that is you have some boundary here, and you shoot in a geodesic into space-time from some anchor point Z into some direction here, and then a certain distance into space-time. So you define dynamically a space-time event like this in terms of such a parameterization, and you can convince yourself that this actually satisfies this condition. And because it transforms in this way, when I evaluate the scalar field at the endpoint of the geodesic, basically under transformations, these F's just cancel, and it's going to be gauge invariant. So and that represents the value of the scalar field at the end of the geodesic. So that's kind of standard in the stressed observables program. Now the question is, can we actually relate that to dynamical frames? And so that's kind of the additional step that we put on this. It's not a huge development, but it turns out to be quite useful. And in this case, you could just, instead of just looking at a single geodesic, you can just look at a whole congruence of geodesics shooting into the bulk, and then you can use basically these parameters as parameters to parameterize bulk space-time points dynamically. And then this map from this space here of parameters into space-time defined by really just this map here, then defined to something that transforms gauge covariantly in this sense here. Now the thing is, of course, we would like to have a dynamical frame field, so a map from space-time into this parameter space. So what we can do is this set of parameters is in general, of course, going to be overcomplete. So if I'm in 4 dimensions, then tau and z will be 4 parameters. W also, there will be 3 parameters, so that will be sort of 7 coordinates for 4-dimensional space-time, so that's too much. But what we can do is restrict to some subset of that parameter space on which this map turns out to be injective. So for example, you can achieve it by just fixing the boundary vector field, so fixing once and for all the directions at which we shoot the geodesics in. And then that defines you, okay, an injective map into some field-dependent sub-neighborhood in space-time on which we can invert it. And because of this transformation property here, this guy will just transform as a scalar. And if I put suitable coordinates on this space, then you can convince yourself that that sets up dynamical scalar fields that are actually constructed out of the metric, just because I'm just using geodesics. And these scalar fields basically assign to each space-time point, the values, whatever tau and z that I use to parameterize the bulk points. And when I do something like this, I can then also rewrite the stressed observable in this fashion here, just basically by pulling back the scalar field to the space OI or O1. And then I can precisely interpret that observable now as a relational observable. What's the value of phi at the event in space-time where the frame is in the local orientation tau z. Okay? So in this way, we can see already that we can interpret these stressed observables as in fact, in a relational sense, as a relation observable. Now, having this map here is actually also very useful if you want to address anything else than scalars. For a scalar, it's sufficient to have just, it's an ultra-local object, so just having a parameterization of a single space-time point is sufficient. But if I want to look at something like vectors or so, then I will in any case need something like this here. So this will then also allow us to construct, for instance, dressings of tensor fields and so on. Okay, now let's move on to covariant relational observables, and basically they work now in essence the same way. Now the aim is here that we have some non-invariant quantity and we want to localize it relative to some reference scalar field degrees of freedom that we build out of our field content. And so effectively what we are indeed looking for is some gauge covariant frame that transforms like this. And typically, with relational observables in the literature, people consider these frames to be built locally out of the matter fields. And but then basically the idea is the same as before. Now we can just take some covariant functional, some tensor field, say, and then we can just frame dress it in this way, and then it just becomes gauge invariant just because of these transformation properties where the f's, the diffeomorphisms will just, the actions will just cancel. Now it's important to note that this object here is now, because I'm pulling it back to the orientation space, it's actually some observable or some object that lives on this orientation space. So here space-time, maybe the neighborhood where the frame is valid, and some observable here that I pull back to this orientation space. And then here in this orientation space, there's no more gauge symmetry. So I have a locally deparametrized theory. You can interpret this here really as as a relational observable that is kind of constituting or answering the question: what's the value of certain components if it's a tensor of A at the event in space-time where the frame field is in a certain local orientation. Okay, now it should be fairly clear then from what I'm telling you here already that dressed observables and covariant relational observables are basically the same thing. In particular, if I allow the frame fields to be general, so meaning they can be built out of matter or geometric degrees of freedom, they can be locally constructed, non-locally constructed. If I allow all of that, then they're exactly the same. And that's typically in HapTH, it's boundary anchored, so you use kind of non-local constructions of frames. And conversely, for instance, in more canonical minded people, they like spatially compact hypersurfaces where you can't do, where it's, you kind of use more locally defined frames. But if you suitably extend the notion of what the dynamic reference frame is allowed to be, then the two notions of dressed and covariant relational observables are exactly the same. 5 minutes. Yeah. Now let's go to this other representation, the so-called single integral relational observables. The aim is basically the same. It's also a covariant representation. Let me just give you a toy example. Suppose we have 4 scalar reference fields that happen to parameterize space-time. Then here one uses an integral to basically answer the question, what's the value of phi at the event in space-time where the reference field takes certain values. And in particular, this form under the integral is indeed a covariant top form, so it's a gauge invariant observable. What's the relation to the covariant representation? It's pretty obvious. In this case, we just set these fields we identified with the frame, basically put that into plug that in, and then we just solve that, the delta function, and then we see, okay, it's just exactly the same observable that we had before for this case of a scalar field and frame fields that are globally defined. Now, you can generalize that also to frames that are not globally defined if you introduce certain characteristic functions that vanish outside the neighborhood where the frame is well defined. And you can also generalize this to smearings of relational observables where, for instance, also you don't peak it with a delta function, but you can smear it in other ways. And that basically amounts to just smearing relational observables in your local orientation space. And you can also generalize it to other tensor fields. Okay, so again, if you allow for these generalizations of these single integral representations, and you just get also exactly that they're equivalent to the covariant observables. Now, maybe as a last topic, let's go to the canonical formulation of relational observables, and this is now a lot more tricky, the relation to the covariant formulations. So here, the idea is to use, in the canonical, basically the ADM phase space, to use some reference scalar fields to localize other dynamical degrees of freedom. And so this hinges really on the relation between the covariant phase space and the canonical phase space. And that's a non-completely obvious relation. It was discussed by Lee and Wald in a nice paper. Basically, the covariant phase space is defined by the field space of covariant field configurations. It has a subspace of solutions that we care about. And the kinematical phase space is basically obtained in the following way. In the covariant phase space, you a priori don't need to choose any Cauchy slice. But when you want to link it with the ADM formulation, you have to choose a Cauchy slice. When you do that, you can obtain a presymplectic form defined on this field space here. Because it's presymplectic, it has degenerate directions. I can mod out those degenerate directions. That defines kind of something like a quotient map. And the image of that quotient map is a space that has a well-defined symplectic form. That's a phase space. That's the ADM phase space. And if you apply that map to the space of solutions, then the image of the space of solutions is just the standard constraint surface in the ADM phase space. And okay, it just so happens if you have some covariant relation observable, by construction it will restrict to 1 on the canonical constraint surface, and that's because it's invariant under along the gauge orbits, and the gauge orbits, they're at least mapped partially in some sense to gauge orbits here. There's some gauge orbit information that's actually not, that doesn't descend down. Those are diffeomorphisms that don't leave the space-like nature of the hypersurfaces invariant. So in some sense it constitutes a partial gauge fixing, but so in some sense you can view that as a partial gauge fixing. But in that direction, it will always work in such a way that the covariant observables map to canonical observables. Okay, and under certain restrictions, you can show that this object here, this canonical observable, can be written in a power series form that's only valid on the constraint surface. With constraints as generators, and these are smeared constraints that basically correspond to the smeared ADM Hamiltonians. And that's, in a nutshell, kind of the stuff that Bianca Dittrich proposed, nearly 20 years ago, so which you can recover. So under certain restrictions, you also get that the covariant and power series are equivalent. So I think I'm running out of time. So this was just to mention that you can also get generalizations of the notion of frames. It doesn't only have to apply to events in space-time, it can also apply to extended objects, such as submanifolds, and in this way, you can also, for instance, understand minimal surfaces or areas on minimal surfaces, such as in holography as relation observables, relative to an extended notion of dynamical frame. But maybe let me not go into this, and I think I skipped the part on frame changes, as I guess time is up. And then I also skipped the part on general covariance, maybe. So yeah, here's the summary. So we basically have now one approach that kind of encompasses basically all of these approaches to gravitational observables, really unifies them, and that's based also on using dynamical reference frames. When each of them is suitably extended, they're all equivalent, and then up to some fine print for the canonical approach. And okay, I guess the other parts here didn't actually even have time to discuss, so let me just leave it here. Thanks.
Yeah, thank you, Philip, for this great overview talk on the relation between these different formalisms. We have time for 1 or 2 quick questions. Yeah, Param.
So in the previous, when you did the covariant single integral, etc., you never made any restriction to solutions, right, to the field equations. But when you, so is there some different, I mean, so something off shell, something on shell, something,
yeah, I mean, at the end of the day,
it's a vague question.
Yeah, I mean, at the end of the day, you also only care about restriction to the space of solutions. So. I mean, classically, at least, that's of course the only thing that matters. So I didn't mention it, but yeah, in the end, you would also restrict at that level. Sometimes in the explicit constructions, it's maybe not so explicitly mentioned, but effectively at the end of the day, because you want to solve equations of motion, you always go to the restriction. Yeah.
We have time for one more question. Steffen.
Yeah, thanks for the nice talk. I was just wondering, so these kind of equivalent statements, whether they depend on the type of matter fields that you're using, for example, Brown-Kukash dust and things like this, which are designed to give you reference frames. Does that improve somehow these statement?
Does it improve what statements?
So you said, for example, for the equivalence for the covariant and canonical power series representations, there was some fine print and certain conditions needed to.
Yeah, so the fine print is a little bit hard to explain in few words, but it has to do indeed with the types of frames you can look at. Then in the frame dressing, there's these maps to the orientation space involved. There's restrictions on those maps for which it works. What those restrictions mean concretely in the case of the Brown-Kukash dust, off the top of my head, I don't know. But it could be that in that case it actually, because it's a very simple reference frame that actually in that case it defines your diffeomorphism, the scalar field. So in that case, I think the restrictions would be, it would satisfy the conditions for mapping this. And for instance, parametrized field theory does too, for sure. But
so Carlos, you had a question. Is it brief?
Yeah, it's pretty elementary. You can.
Okay, let me do it in the discussion session. Let us thank Philip again. So take your time. Do you need a microphone? 5 minutes before.
Okay.
Okay. Does this work? Okay.
So let's start with our second talk, and we have Michael Roof here from Radboud University, right?
It's UCLA.
Oh, sorry. Okay. I know. I'm from UCLA. I'm very sorry. So, classical observables from quantum scattering amplitudes. The floor is yours.
Okay. So let me start by thanking the organizers for having me here. It's very nice to be in this somewhat different setting. And I come from a bit of a different background, so if there's questions, of course, we should discuss later. This is meant to be very superficial in some sense. All right, so the topic of this talk is going to be classical observables from quantum scattering amplitudes, and it's based on work I've been doing during the past few years together with a host of different collaborators. Now, I have to start by maybe a quick disclaimer. There are not going to be any results on quantum scattering amplitudes or genuinely quantum results in this talk. The topic of this talk is going to be more that a quantum viewpoint can be extremely healthy for doing classical computations. So let's jump right in. The motivation for this line of work is gravitational wave physics. Of course, one of the most interesting things we have learned in the last 10 years are that gravitational waves are a real phenomena in nature. And they come basically from all different kinds of physical objects that you can think of. For example, recently we learned that there's also a gravitational wave background in the universe. And there are many systems that you can look at, and the most interesting historically have been gravitational binary systems, and these are going to be the main topic of this talk. And the physics goal of this line of research are also pretty rich. For example, you can do this to use this to do strong field tests. You can make you can do cataloging of black holes. You can do tests of the neutron star equation of states and so on. So right now, this is done by ground-based observatories, namely the LIGO, Virgo, and the CACRA collaboration. There have been around 100 events that have been observed so far, and just recently the fourth run has started for these observatories, and they promise that they will give us about 200 more events in the next few years. These experiments are actually very impressive. They're very precise. They measure these things to about 1,000 cycles or more. The length changes are also pretty mind-boggling, and we have very good control over the experimental errors in this setup. What this line of research that I'm working on is actually targeted more is the next generation of experiments, which we will see around 2035. These will have order 10 to 100, a factor 10 to 100 improvements in signal-to-noise ratio. And in particular, this will also involve a far bigger reach and greater sensitivity, and therefore more data. And we will also be able to see extreme corners in phase space, in particular with the space-based missions such as LISA around 2035. In principle, all of this can be done numerically. In the past 15 years, people have understood quite well how to do numerical relativity. The problem with this is that it's still relatively costly. A typical numerical relativity template can take up to 10 to the 5 CPU hours, typically for the first observation. And we need lots of these templates because it's done by some interference measurements. For example, for the first detection, 250,000 templates were needed, and this basically means this is far too much to do with numerical relativity. It becomes even harder if you go to certain corners in phase space. A particular example is this large mass ratio limit, which will be important for LISA. Here we will see like a factor of a hierarchy of 1,000 to 10,000 in between the masses, and this is just very challenging for numerical relativity to do. The solution to the problem is that one uses partially analytic information, for example, post-Newtonian physics, which is a fully analytic approach, or the so-called effective one-body approach, which uses partly numerical relativity information. And in all of these, key input is, for example, the perturbative correction to the Newton potential. Now, in this talk, we're not going to focus on the in-spiral problem, where two black holes coalesce, but we are instead going to focus on the scattering event. This might be a little weird to look at because, for example, if you look at the signatures of these types of events, in-spiral event has a very characteristic signature, which is easy to detect in a detector or filter out from the background, whereas the scattering event looks rather boring, so it's very hard to detect. And we are also not really, it's unclear how the event rates would be for such events. So it's very hard to make any predictions whether we'll be able to actually detect these things in the future. So the reason why we're looking at this is more to get some better understanding of how these things look like. And in particular, scattering is arguably one of the simplest processes you can look at in any quantum field theory. And it's very beneficial to look at both for numerical and analytical approaches. It's also a problem that can be treated fully in a perturbative setup, so we don't have a merger, which might sound boring, but it's also very nice to keep the problem clean. And there's a very close relation in between the bound and the unbound problem. Sometimes people think about this by some kind of analytic continuation. All right, and for us, the one important point is that it measures very naturally with a scattering amplitudes program. All right. Also, just to say that this doesn't really happen in vacuum. Also, people in classical GR are very interested in the problem. We also heard earlier from Knorr that also people in this community are interested in scattering, which is also very encouraging for us. I can maybe highlight really quick that we had a recent study of this, and we were comparing with what's called gravitational self force, where you take the limit of one mass being much larger than the other. And what we were able to do is we could find, with this semi-analytic approach, we could find that the approaches are very complementary and that one approach can help the other. And by combining them or by comparing them, we find that we can actually do this perturbative computations to a very high order, up to the percent level or even better. Because this is an observable-based session, I can maybe highlight a few observables that we are concerned with. The basic one is, of course, the waveform, which looks like this. Another one is the scattering angle, which is personally our favorite observable to look at. We have radiative losses. If spin is involved, we have the so-called spin kick. So the particles will change the orientation of the angular momentum during the process. We can look at the time delay, and we also have things which are maybe a bit more academic because we don't have like a full angular resolution of the problem, but we could also look at things which are so-called event shapes. Now, the problem can be treated with perturbation theory. If the particles are separated very widely, there's a natural expansion in a weak field. We can just solve Einstein's equation perturbatively. This was already featured in JJ's talk earlier. If you try to do this, so this naturally leads to Feynman diagrams or to a Feynman type diagram computation. But the problem with this is that it introduces, depending on the gauge, it introduces very complicated Feynman rules. And this very quickly grows out of hand. If you just do like back of the envelope computations, you see that at some point, maybe not at the present order, but at some point this will be very intractable with Feynman diagrams. And this problem is, of course, very familiar in other corners of physics as well. The problem, the solution around this is by adopting an on-shell perspective on the problem, focusing on scattering amplitude. Maybe just to highlight this very typical example that we like to give. If you're trying to compute some scattering amplitudes for gluon, for example, 2 gluon goes to 4 gluon, which is something that at some point was a state-of-the-art computation. You'll find that this computation leads to a result which is basically 15 pages long. But if you take an on-shell standpoint and you compute the on-shell amplitude, you will find that in the right variables it only collapses to a single line. So this really tells you that the objects of interest might be much simpler than what you have in intermediate expressions. In general, the objects we're looking at are also highly constrained by symmetry and so on, which will be important to do these computations. Now, how can we leverage this to make a classical computation? People have figured this out quite a long time ago. Of course, if you can compute the quantum S matrix, you should have all the information about the classical S matrix as well. Basically, this work was the first work where this has been done in 71. And people have been using this at the time to compute the first subleading corrections to Newton's potential. This is a very nice idea, but at the time, people didn't have the tools to really push this to very high orders. So it didn't really gain any traction at the time. So there's really only a few papers around that time that study this. And this is the basic point. If you want to convince people, you have to do something new. In the meantime, we've become much better at these computations. And this is also why recently there was an increased interest in revisiting these computations, which was also urged by the gravitational wave community. Briefly, the setup that we're using. Quantum gravity is encoded in, we're just using some low energy effective field theory. And also in principle, we're including finite size effects for the particles. So for example, if you have a neutron star, we can all encode this in higher dimension operators. But in principle, the process we're considering is scattering of point particles in Einstein gravity. At some point, it's very important to include these operators, but this is just a technical caveat. And this can very easily be extended to include the spin of the particles as well. The classical limit, which we eventually want to take, is dictated by the correspondence principle. We have a very strong hierarchy of scales. Basically, the angular momentum of the system is very large. This is really, if you go to natural units, you will have like something like 10 to the 40 orders in this parameter. So the natural expansion is really in small j. The hierarchy of scales can also be phrased as having a small Compton wavelength with respect to the Schwarzschild radius, which in turn should be much smaller than the impact parameter to have perturbative expansion. And we will be interested mostly in the long distance physics, which corresponds to Stroff graviton exchange. And in principle, the rule is that the graviton exchanges will be of order h bar, but we will consider processes where there is basically a 1 over h bar times of these exchanges, leading to eventually a order 1 result. This was already quickly mentioned. The basic building block for computation are 3-level amplitudes. JJ told us about the double copy, so I won't give you much details. The basic point here is basically we are very efficient at computing these 3-level amplitudes. Now, as I was saying earlier, the amplitudes are very highly constrained by the structure, and this can be leveraged to compute loop-level amplitudes from 3-level amplitudes. And this is done by the method of generalized unitarity, basically constructing an integrand from the residues. And so if we are very good at computing 3-level amplitudes, we are also very good at computing loop-level amplitudes. And this has been shown to be very efficient and in many different contexts. For example, in supergravity up to the 5-loop orders. Once we can compute an integrand, we have to also perform the integration. This is a separate step, as was also mentioned by JJ. We, in general, have to deal with Feynman diagrams. And the way we deal with them is in a very standard procedure from collider physics, in a 2-step procedure, which first requires integral reduction, and then the evaluation of the remaining integrals that remain after reduction. And this is well understood, and it basically leads to a problem in linear algebra, which we can solve by making use of computers. The remaining integrals satisfy Fuchsian differential equations. This is also a very standard insight from collider physics, and there is a vast literature on how to solve these integrals. The key point is it's basically very important in all the steps that you always have to take the classical limit very, very thoroughly. And in this case, the classical limit leads to a reduction in the number of integrals you have to compute, but it also makes the problem much simpler because the number of variables drastically decreases. So the full problem depends on both the masses and the energy and the impact parameter, basically, of the scattering, whereas the classical limit only depends on a single variable. And also the resulting functions become much simpler in the result. Just to prove. How much do I have? 5? Okay, cool. Now, once you have the setup for the amplitude computation, the question is, what can you do? Like, if someone hands you an amplitude, how to extract the classical physics from this? And the basic problem here is that amplitudes are themselves not observables. This is something that's very well known, of course, also to people in collider physics. There are IR divergences hiding, and also what is maybe a bit more pressing is that the amplitude as expanded in the classical limit itself doesn't have a well-defined limit. Basically, if you increase the number of loops and you do the power counting properly, you will find that each higher loop order diverges even more strongly with 1 over h bar. And the question then is how to deal with this. There's a bunch of different approaches how to do this. One possibility is to basically do a matching computation to determine the scattering potential, starting from either the Schrödinger equation or the Lippmann-Schwinger equation. And in this approach, you will find that the divergences match. And this has been the first, or for a long time, this has been the most prevalent approach. It's very nice because it's very close to what the analysis actually wants, because the output of this computation is the potential. The small issue with that is that the potential still is not really observable, so it still carries some coordinate dependence, which we don't really like. The maybe more scenic approach, and this is to quote the authors of this approach, is to go directly through observables. Then we basically know that all the divergences should cancel from the observables, and we can take the limit h bar goes to 0 just at the level of the observable. It's basically just something you can go through the steps very, very easily yourself. You just define a difference in an observable in between an asymptotic out and an asymptotic in state, and you can find that you can relate this quite straightforwardly to scattering amplitudes. And this is something that's very, very tractable in practice. And it's very similar to what people would do in collider physics. This has been done to obtain a bunch of new results. So the radiated energy in the process, the radiated angular momentum, waveforms, which is a pretty recent development, and also observable with spins. And exactly, and in principle, it's also very straightforward to get more differential observables. So, for example, like angular distributions and so on out of this kind of framework. There's another way how one can deal with the divergences, which is basically one can resort to unitarity. The divergences should exponentiate, and one finds a phase which contains all the classical physics as well. I don't have time to discuss this here. Eventually, what the aim of this program is to push this to a very high order. The more recent version of this program is very efficient as compared to what people had in the 50s. There were many state-of-the-art results that we've produced with these results. There's like many hundred papers by now in the last few years that have been written on the topic. Spin has been considered at the order g⁴, and radiative effects have been included as well. The question, or basically what we want to do, is we want to push this computation to even one higher order. This has a multitude of reasons. One of them is, for example, as I was discussing in the overlap with the classical computations, to do better benchmarking or to improve hybrid models, or to relate back to the bound problem. The problem in pushing these computations to higher order is that basically around every corner, we also saw this in JJ's talk, there's exponentials hiding. So you might be deceived by the fact that the 3-loop order is relatively easy with all the improvements that we made to the problem. But the 4-loop problem is very hard, and basically the reason for this is just the number of integrals and so on just explodes. So we need some new ideas to tackle the problem. And what we recently did in order to get some handle on improving and making these computations at the next order is by going to a simpler problem. And what we did is we considered scalar electrodynamics at the 5th order in the fine structure constant. And by this, we basically showed that 4-loop computations are actually possible in the setup. And we are very confident that we can leverage what we learned from quantum electrodynamics to gravity. So there's a lot of overlap in the computations, and we also made more progress since we put out this result, basically. So maybe with that, let me conclude. Maybe the main point of this talk is that scattering is a very interesting process that people should look at. It provides a very clean environment to study, and that should help with clearing up conceptual issues. There are many issues in the classical GR community that are still floating around, and actually that prevent even from incorporating results into the pipeline for LIGO and Virgo and so on. There are many observables that one can consider. We have constructed classical observables by using a quantum object, a quantum scattering amplitude, and we have used a manifest on-shell setup, which is very helpful because it avoids all the algebraic complexity and the gauge dependence that one would find if one did the computation in a different way. We have many new results, and the program is instrumental in pushing the progress in the field. And maybe the last thing is that we took a lot of information from collider physics in putting together this framework. It would be interesting to see if there's other corners of physics that could teach us something. And I think this might be a place for the community here.
Yeah, thank you for this nice and very elaborative talk and new perspectives. Are there questions? Okay. Up there.
Yeah, thank you for the nice overview talk. So two things. So when you say millions of integrals, this is the number of master integrals, I guess? Or
no, the number of master integrals is around 4,000. So
okay, 4,000. Okay, that sounds a lot better. And when you said, so you mentioned special functions. At 3 loops, you get elliptic or integrals that are elliptic.
Yes.
Have you identified what kind of special functions or what kind of geometries
We
there
are
appear?
in the process of doing that.
See, okay.
I mean, we can discuss, but yeah. We can discuss.
Okay.
No, but
Yeah.
maybe,
Okay.
no.
I don't see a further question, but just briefly, can one compare, or do numerical relativity calculations exist of these scattering processes?
Yes,
that you
yes.
can
I think
compare
this
to?
was actually on the slide and probably just skipped over it. There's actually also overlap with numerical relativity, and in principle, there's like this picture where we have different frameworks. So one of them would be this. I don't have the plot here, but one of them would be the self-force, which is particularly good in one corner. We have the perturbative approach, which is good in another corner, and then you have the corner of phase space where you really have the non-perturbative physics, where you really need numerical relativity. And people have been really recently, people have been doing more numerical relativity results, more numerical relativity computation. As for example, this one plot here from Damour and Retegno, where they compare to numerical relativity and also find percent level agreement in between what we are doing and what they are doing. So that's very encouraging as well.
Anyone else with a quick question? Otherwise, let's thank Michael again.
Okay.
After this talk. Okay, and let's start with the final talk of this afternoon session before the discussion. And I'm happy to introduce Christoph Mintz from University of York, and he's going to tell us about algebras and states for quantum fields on causal sets.
Yeah, thank you for the introduction, and thanks also to the organizers to have me here. Actually, well, the research I'm presenting is from the University of York, where I was doing my PhD. Currently, I'm actually in Germany doing my first postdoc. So I'm going to present some quantization method that is actually meant to, or I presented for a finite dimensional setting, but you might also apply it to other settings. And for that, I'm going to start with motivation and use causal set theory to construct a particular example that I will then elaborate on this method afterwards. So first, to also have in this session a bit of causal set theory. What is a causal set? Those of you who don't know about causal sets, well, it's just mathematically it's just a partial ordered set with the additional property of being locally finite. That means that whenever you take any interval in this partial order, you get a finite set. And diagrammatically, this is quite often drawn as with these Hasse diagrams, where you have essentially time going upwards, like you usually do in space-time diagrams. And the causality is very similar to a space-time. So even a space-time can also be described as a partial order, but it's not locally finite. And here I just take an example. This is a 3-simplex, so this is the simplest causal set you can imagine that embeds or needs at least dimension 4 of Minkowski spacetime to be embedded. Now I want to do a scalar field theory on that as a simple example. So I just take all the vertices and I define a field on that. So for this finite dimensional example, in fact, this is just something that's isomorphic to Rn, where n is the number of points I have. And to get the algebra of classical observables on that first, we take then functionals of these fields. So any functional of that gives us, in the algebraic sense, the algebra of classical observables. And you can equip this additional to the point where it's addition and multiplication for the algebra. You can also equip it with a Poisson bracket. This is so far off-shell, because we haven't imposed any field equations yet. And you can find more in this paper here. Next, we now want to impose the field equations to go actually on-shell. So what you first have to do, you take your field equations that you might know from your favorite spacetime, and you need to discretize it. So, for example, for the scalar field theory, we have the Klein-Gordon field equation that we want to discretize, and this means that we usually take any point and look into its past, and the past then split it up into several sets, and these sets are then used for the discretizations. And there are different approaches to that. But all of them usually boil down to taking several subsets and discretizing this in this way. And then once we have done that, we can actually invert this operator that we get. So essentially, this is just for a finite setting here. It's just a matrix, so we invert this matrix, and this gives us the retarded Green operator. And then with this, we can also construct the advanced Green operator and the Pauli-Jordan operator. And that will then be essentially the operator that is necessary to get any solution. When we take the image of this operator, this is actually the same as the image of the off-shell Poisson bracket that I've shown before, and this gives our solution space. But this so far was only to motivate one example that you could think of. So now to something completely different. Well, actually, it's not that different, because, as I said, you can use that causal setting for the following construction. So far, everything was classical. Now we want to go quantum, and usually a few methods that you could think of to quantize are deformation quantization in the formal way on causal sets. It has also been done in this paper here. You can also do strict deformation quantization, which is a bit more mathematically involved, and there are further many other methods. But what I want to talk about is geometric quantization, and in particular, I will highlight these 3 points that we will need to get a quantum algebra for that. So we will start with this finite dimensional setting. In particular, now a bit more general, what we have as an input is just a 2n dimensional vector space. Symplectic vector space, so it has a symplectic form, and also it has an inner product. So these are essentially just our ingredients, and we can relate the symplectic form and the inner product together. Then we have this operator. In this setting that we had before for the causal sets, that is actually very closely related to the Pauli-Jordan operator that you've seen. Just to give you some idea what these symbols mean. Now I will say what the quantization bundle is. Well, the quantization bundle is we have our phase space, our symplectic phase space, and now we quantize, we define a Hermitian line bundle on that. And this Hermitian line bundle, of course, has a curvature or a connection first, and this connection, the curvature of this connection is then directly given by the symplectic form. And in that sense, you can do the same procedure for any Planck constant. So in the following, I will actually consider h bar as rather a mathematical parameter. So you can tune h bar, and in the limit h bar goes to 0, you actually recover the classical case. Now this is only the quantization bundle. Now we want to choose our physical Hilbert space. And this physical Hilbert space is usually taken to be some subbundle of this quantization bundle. And one way to choose that is, as we will do, we choose a subbundle by looking at the spectrum of the so-called Bochner Laplacian. So this is a Laplacian which you can define with this connection from the quantization bundle, and this is in that form. And then we just look at the spectrum of that. And if you look at the spectrum of that, in particular for this finite dimensional setting, what do you get? You get some spectrum that looks a bit like that. Well, this is just for 2 dimensions, but if you can also increase the number of them dimensions. And what you might notice here is that you have one lowest eigenvalue. So this spectrum is actually all positive, and you have some eigenvalue down here, and then you have a spectral gap. And in more general settings, so whenever you didn't start with a finite dimensional setting, but or with more an interacting field theory, because so far I've been talking about free scalar field theory. So you might also do this for interacting field theory. Then what you would get is, instead of a symplectic vector space, you would get a symplectic manifold. But you can there has been some paper about this, where you could also make an argument about some bounds on the spectrum, so that you can also isolate some lower part. And we take this lower part of the spectrum to define our physical Hilbert space. We isolate that, and then take all the sections all of this line bundle that correspond to the eigenvalues or the spectral part here. And explicitly, I've written down some formulas here, but maybe they're not that important. So these formulas are essentially what you would get for the finite dimensional setting. You get just some. You can choose some complex coordinates on your phase space, and then what you will get is holomorphic sections on that. Now to the last step of this. So now we have our chosen Hilbert space, and now we can just define our projector, so a projector to this Hilbert space, and we can use this in a so-called tuplets quantization to map from our classical algebra that we have constructed before, or we had given before as functionals. We can now map to, well, if you take Schwarz functions here only, then we map to compact operators. But this can actually also be extended to bounded operators on the Hilbert space. But the fact why I take Schwarz functions here is because now I have my quantum algebra that I get here as the image of this map. But I actually want to also construct states on that. So this is actually the other very important thing in algebraic quantum field theory. You want to have states. So I define myself a measure that is essentially then been used in the next step to define the dual operation to this quantization. So we have seen this tuplets quantization, which is essentially starting from our classical algebra here, that I've represented with this disk here, and we map it into some quantum algebra, and you can imagine multiple quantum algebras with different parameters h bar. And then mapping back we can use this measure, which is implicitly defined through this trace, to define a dequantization map. Well, now this dequantization map gives us again a classical observable corresponding to some quantum operator, and we can now use this dequantization map to actually define a state. So in the algebraic sense, what is a state? Well, a state is a functional that takes in any observable, any quantum observable, and spits out a complex number. It has to be positive and normalized. And if you do this with this dequantization map that corresponds or is dual to the tuplets quantization map for this finite dimensional setting, in particular for the causal set setting, then what you will find is actually the Sorkin-Johnson state. So it turns out that the state you can define with dequantizing and then evaluating at the 0 point of your symplectic manifold. Yeah. Is then giving you this state, and this is the Sorkin-Johnson state that had been known in causal set theory before, but essentially what we did in this project was find a mathematical way to define the state. So so usually when you look into the literature about the Sorkin-Johnson state, then you usually find some sort of 3 axioms that are imposed on on an operator that essentially gives you a 2-point function, and that is then this 2-point function that corresponds to this state, what we have derived here in a more mathematical way. It was also interesting that this state has actually been suggested to also be to be used to do quantum field theories on curved spacetimes. However, if you do that, then you have to be careful because the state is not Hadamard. But there are modifications that reinstate this Hadamard property, and there are also similar generalizations actually to Dirac fermions. And with this, I will actually come to my last slide. And on this last slide, I give you a summary. But so I summarized the steps again that have been taken so far. But I also again want to motivate that this can be also used to generalize the entire procedure to interacting field theories. So in the case of interacting field theories, you would start with again with a Poisson bracket, and you can actually use the free Poisson bracket of your free field theory and modify it with Möller maps, as also been mentioned in this paper here. And then you can follow the same steps of the procedure that I've been talking about. So you can take again the image of the solution space, and then you can define a symplectic space. In the case of the interacting field theory, of course, this symplectic space is now a symplectic manifold. So it's a bit more complicated, but we can still use this spectral condition what we have seen to single out the physical Hilbert space. And with this, we can then use the Buchner. This is what the Buchner Laplacian is used for, and then we can go to this physical Hilbert space and can use the projector to that to define our quantum algebra. And if we can find a dual, so this measure which I've showed on a slide before, then you can find a dequantization map, and with this you can again define the state in a similar fashion. But that is something that we haven't finished yet, so we are actually thinking about this extension to interacting field theories. And with this, I thank you for your attention, and I'm here for questions.
Yeah, thank you for this nice talk on causal sets and matter. Are there questions for Christoph? Philip?
Yeah, thanks for the nice talk. So I'm not sure if it's terribly relevant for the whole program, but I didn't quite understand, even at the beginning when you were talking about fields, classical fields on your causal sets, where does even the free Poisson bracket come from? Is it that you take some, because it seemed like you were taking some kind of algebraic point of view, or you consider it as like a C-star algebra and then you look at flows and
so there is the notion of the Piles bracket you can define. Yeah, that is a Poisson bracket. Yeah.
More questions? So maybe I have a brief question. Mm-hmm. So your construction, does it rely on particular causal sets? So do they have to be manifold-like, or can this be like...
No, so the causal set setting was really just to motivate this construction. But as I said, I mean, the ingredients for this quantization construction are just that you have a finite dimensional, in that particular case, a finite dimensional symplectic vector space with this inner product and the symplectic form. But the idea actually is to even do this for any symplectic manifold. Then you would have a Riemannian metric instead of the Riemannian metric instead of the inner product, and you would have still a symplectic form on that. And these three ingredients, or these two ingredients, essentially, you can use to construct this. Yeah.
A quick question before we go on to the discussion session. If that is not the case, let's thank Christoph again. So now we have a bit more than half an hour for the discussion session on observables, so we can open the floor to questions to all the speakers of the session. So does anyone want to start? Yeah, because you had a question before, so...
Hi. Well, this is a question for Philip. Well, perhaps it's a pretty elementary question, but it's a question that I have from a long time. Why, when people compute things in general relativity, they usually don't pay too many attention to characterize things in a relational or in a gauge invariant way? For example, in element. Oh, it's working? Yes. Okay. Oh, okay. Thank you. For example, when you calculate something pretty elementary like the deflection of the light by gravitational fields, you don't characterize the angle of deflection in a gauge invariant way. So, and it's very usual in people doing, for example, numerical relativity. They don't pay too many attention to characterize things in a gauge invariant way. So my question is, why?
Yeah, that's a very good question. And classically, indeed, you don't really have to do that. You can just do gauge fixing, and then any of these manifestly gauge invariant approaches, I mean, as long as you do a suitable gauge fixing, that will just agree with what's usually done in textbooks and so on. Once you compute predictions in a suitable gauge, I mean, they're physical. Now the question is, what do we do when we go towards quantum gravity? Then possibly this gauge fixing or choosing suitable coordinates may not be present, and then actually having gauge invariant objects is something that is very useful. So it's in fact, in some sense, more useful for going beyond the classical case. And for conceptual reasons, it's also nice. I mean, there's using this gauge invariant framework, you can also put, for instance, notions such as general covariance in a more physical setting, something I didn't manage to cover. But if you're strictly speaking about predictions, then gauge fixing is good enough.
Okay, thank you.
And or maybe just to put it this way, basically relational observables, what they are is they're gauge invariant extensions of gauge fixed quantities. But then that just means, on my gauge orbits, I can evaluate, or basically I look at some gauge fixed quantity somewhere on that gauge orbit, and then I just extend it in a suitable way across the whole gauge orbit such that the observable takes the same value everywhere along that orbit, but the value it takes is the same that the original observable took in a particular gauge. So in that sense, the numbers will just agree.
Okay, everything now has sense for me. Thank you very much.
Yeah.
Are there more questions for our speakers? So maybe I try to speak to you, Philip, again, because you mentioned that you motivated your framework also to say that you wanted to build phenomenologically interesting observables. Do you have something in mind for that?
Well, yeah, I guess any observables that could be tested in experiments. I mean, I guess even one could ask these questions perturbatively. For instance, one could even ask formulating the phenomenologically very relevant observables that Michael talked about. In principle, you could also discuss those in a gauge invariant context. Though in that setting, since it's perturbative, you would have to basically restrict this gauge invariant approach to a perturbative setting, but which in principle is possible. But of course, for us, there was more the motivation of having at least a general framework that can handle, at least in principle, whatever a gauge invariant observable is. So we had a somewhat broader question to start with. But then once you have such a framework, then you can ask, of course, more specific questions about particular solutions or so, where you might want to, consider what sort of concrete observables we might want to write down, which would be examples of the type of what I presented.
A question actually to both speakers, both Philip and Mike. If we pretend that scattering amplitudes are non-perturbative, or whatever way we calculate them, would you do comment how they can fit into approach of again, gauge invariant or relational, because implicitly when we scatter some, we have in, we have out, we assume some reference frame and certain choices. So it's a bit like invariant observables where we fix things on the boundary. Can you comment more on potential relations?
Do you want to go first? Or
I mean, from my side, I can only say that if you had a fully non-perturbative scattering amplitude, it has, of course, more properties, maybe, like there's additional information in there, but it like in for example, this observable-based framework, you just put it in and you get the non-perturbative observable out from that. And then I'm not sure, yeah. So, yeah.
Yeah, I mean, you know, these observables, they will fit. I mean, like scattering matrices and so on, they will fit into this relational observable program, but I would think of it more in a perturbative setting, you know. Yeah, but
in theory it's easy.
Yeah, in practice, okay. Yeah, how you do that in practice, I haven't thought too much about it. But there exists a paper by Don Merrill that kind of touches a little bit on that, but in a very preliminary way. So it's I would say overall an open problem how to really relate relational observables and scattering amplitudes, scattering matrix.
More questions from the audience to one of our speakers. So, Michael, something that I was wondering about is there a connection also to effective field theories, like where you would try to treat gravity as like a perturbative quantum field theory, and you're looking like at like the low energy quantum corrections?
I mean, this was on one of my slides. This is the basic setup that we're using. We never go beyond the leading order in principle, but you could include the higher order, the higher derivative operators.
Yeah, that's what I meant. Like, do you include R squared and such terms?
So we in our like in our works, we usually were concerned with the classical part of the computation, but people have studied this, like for example, contributions of these high derivative operators to certain observables like time delay and so on. There's this in the literature, yeah.
Renata? Just wait one.
That's a question to Philip. I wanted to ask you if you have an intuition about which of the three different setup to construct relational observables is more fitting in order to make contact with cosmological observations.
Well, I would say since they're equivalent, it doesn't matter. But
That's fair.
But you can ask the question of which one is maybe the most convenient one to use overall, and I find the covariant one the most convenient. And that's just the simplest way of I mean, once you have such a reference frame, the simplest way in which you can dress general tensor fields, and in fact you can even, I didn't discuss that, observables or kinematic observables that are not gauge covariant, so you can even generalize it beyond that. So yeah, it's just much simpler in that setting than, for instance, in the single integral approach, or in the power series construction. Talking about tensors is actually a little bit complicated.
Then I have a follow-up question. If you try to make contact with cosmological perturbations, then I have a conceptual, like a bit of a confusion if then the perturbations are defined on your reference fields, on your background structure or coordinate structure. Is there some ambiguity, or there is some preferred way to do that?
Well, there is, of course, an ambiguity in the sense of which frame do you choose. And although you're going to be gauge invariant, you're going to be frame dependent. And so, but the thing is that this convention of which frame you choose isn't actually a gauge fixing in the usual sense. So these frame change maps that I actually didn't have time to talk about, they're not gauge transformations of the theory in the sense of, so in contrast to coordinate changes, fixed coordinate changes, which map to gauge directions on the field space, which lead to degenerate directions of your pre-symplectic structure, these ones don't. So you can think of these physical frame changes basically in the same sense as in special relativity or special relativistic field theories, where it's, changing Lorentz frame is a change of convention, but it's not a gauge transformation. It doesn't amount to degenerate directions on field space that you factor out. So you can think about it in the same way so in some sense, once you deparameterize your series using dynamical frames, you're kind of special relativizing general relativity in some sense.
I had another question for Michael. So you touched about this on very briefly, that you are, at the moment, you're really only computing like scattering angles, or, I mean, not non-bound systems essentially, which is of course not what you would ideally like to. And you mentioned that there's, well, okay, maybe you can expand, I don't know, because I don't know, how do you go from essentially the potential that you would get, for example, for the scattering event to the potential that would be relevant to compute waveforms or in spiral or bound states, let's say, in the end. Right. So what exactly is involved there, or is this, to what extent is this solved?
I'm not sure how familiar you are with the status of these things. So this is, of course, a very complicated problem at some point. Up to the previous order, it's, or like to the order G to the 3, it's possible to the instantaneous potential is a well-defined object, so you can just transport that to from between the, I mean, it's the same potential. The Hamiltonian is universal, but once you go to the 3-loop order, you'll find that the instantaneous potential by itself is not well defined. It's divergent, so you have to compute a more inclusive quantity, also including radiation modes. But that thing then is not universal. It depends on the structure of the object you're considering. So, and in particular, there's this story with the memory effect that's very closely tied with that. So, so for that things, I think still the understanding hasn't improved too much in the past few years. But yeah.
More questions? So maybe a question for Christoph. So I was wondering, can you compare your, I mean, you mentioned the scalar field in the beginning, and people previously defined, for example, D'Alembert operators on causal sets. Is there a relation to those previous attempts, or can you generalize also these constructions, I mean, these very formal algebraic constructions, to more general matter fields?
Yeah, so as I've shown in the end, I mean, the state what we construct, that is a state that is kind of already known in causal set theory. So this is essentially just a more mathematical way to construct the same state without necessarily using the axioms. So they are implicitly in there. But the way you discretize your fields does not really matter too much. I mean, this gives you then different operators, maybe, so the different relations for the symplectic form. But I think this would be just amounting to some changed constants, at least in this finite dimensional setting.
So that you have a few ambiguities in the procedure in principle, but the qualitatively it's not too different.
Christopher, I have a very elementary question. Early on, you mentioned that embedding of this causal set is possible in 1+3 or higher dimensions. So what technically roughly goes wrong if you try to do it with 1+1, for example?
Well, you can try. So the dimension. So I've said that this would only embed in like. So if you take Minkowski spacetime. So if you really want to embed it in flat spacetime, then it depends like how many dimensions you have. So. Well, as a subset of one of these graphics, you have this sort of crown, for example. So the crown is one that needs 2+1 dimensions, and I mean you can just try to draw it. So if you want to embed this in 1+1 dimensions, well then you would need to have another link between the two central elements, and because you don't have this link, You can't do this. And you can actually try to visualize what is actually corresponds to. This is essentially corresponds to two triangles if you try to draw them symmetrically. So one in the first time slice and in the next time slice. And that's why you have all the simplex there.
Okay, so I have a question for Christoph as well. So in these discrete approaches, when you couple matter, there is the very often question about how to couple chirofermions in this type of theories. And as far as I know, in the loop quantum gravity community, there is a debate about if there is the doubling problem or not. And in your case, I mean, you just said that in principle you can discretize the matter field and couple to. Is there any idea about how to couple chirofermions in a causal set scenario?
Well, as far as I know, there is not very much done on this topic, but I must admit I also don't know about the details of those things that have been published before. But this is definitely an interesting question on how to like encode fermionic fields on causal sets, or even like with some properties of the causal set. So to connect this more to a quantum structure in the spacetime itself, because otherwise causal sets are rather like a discrete model of spacetime. So they are not, in that sense, not quantum spacetime yet. So they're just discrete gravity.
Yeah, I think the problem with chirofermions is that it's already at the level of the discretization. So it's
yeah. So there would probably be an influence directly between the causal structure then that you have to this.
Thanks.
Yeah, maybe only to extend on this question, Antonio, in loop quantum gravity last year there was a paper by Mushin Han and other people where they showed that this fermion doubling part was exponentially suppressed, and I think this was mostly because they looked at superpositions of different space discretizations. Okay, more questions. You can also raise your own points that you always wanted to ask these experts on observables. Also, the speakers can ask each other questions if they want to.
Maybe I have a question. So, do you think so? What would be the most like experimentally falsifiable observable that you could think, where you could also say, well, maybe that sort of theory of quantum gravity is favored over another? Is there something like that?
So you're asking about quantum observables now?
Yeah.
So. Yeah, is there one observable that clearly favors one over whatever the outcome, that favors one approach over another? That's hard because one, first of all, has to come up with observables that have a meaning in different quantum gravity approaches. And so, you have to be able to somehow promote some of these observables into the quantum theory via whatever quantization technique, which will depend very heavily on whatever your approach is. Or maybe you may even want to compare genuine quantum observables that are not even classically definable in this way. But yeah, I'm personally not so aware of any good candidate that would be, common to many approaches that would be viable for phenomenological purposes. I mean, there's of course certain observables such as spectral dimension or so that are studied in many different approaches to quantum gravity, but I don't know how phenomenologically accessible something like that is. So I guess you're asking about something that would be phenomenologically accessible. And I mean, presumably the observable should have some connection to classical observables just because our universe appears very classical on large scales. But yeah, I mean, in one way or another, probably cosmology is maybe your best playing ground, and then for that, it would be sufficient to look at perturbative observables and maybe relating it to the CMB. That's something that, I mean, in principle, of course, all approaches to quantum gravity should somehow relate to. You know,
Yeah, on that note, actually, I think you can look at quasi-normal modes in the decay of merging events. And then with LISA, we will be able to detect them eventually, and depending on your cosmology, you can assume that you will have this black hole echo effect. I don't know if you heard of that, which tells you basically that the quasi-normal modes will be reflected by the horizon of the black hole, and we will at some later time pick them up. And what frequency these quasi-normal modes will be, what frequency we will actually measure, that heavily depends on the theory of quantum gravity. So for instance, in low quantum gravity, you will have like a phenomenological constant which enters this frequency, like this discrete frequency spectrum, and in string theory you might have some smooth behavior, like some smooth decay of reflectivity of depending on the frequency of the wave. So I think this will be, well, not soon, but in 10 years, hopefully, when LISA will start, this will be a real chance to see that actually.
Yeah, I agree. I mean, I guess black hole observables are, in particular, that are detectable by gravitational wave detectors is another good playing ground, yes. Great.
So, Philip, just a question regarding, well, let's say notation. So when you say observables, you mean simply gauging variant objects?
Yes.
Or you mean something that you can go to the lab and measure?
Yeah, so I would call that a question of terminology, not notation, but
okay, yeah.
no, but yeah, you're right. I mean, the observable is understood in the sense of in the crude sense of just gauge invariant objects that could, you know, in principle, that have physical meaning in the theory, but of course whether they are then actually observable in experiment is a wholly different question. And in some sense, calling those observables is indeed a bit of a misnomer. There are other suggestions, I think, going back to John Bell or something, like calling them beables or something like this. That's
Can you speak louder?
Oh, was that not okay? I don't know what you didn't understand, but
that's part, the Bell part, yeah.
Oh yeah. So I mean, there were proposals for calling what I called observables something else, like beables or something like this, and just to distinguish them from things that are actually observable in experiment, and probably is a good. It makes sense to distinguish them, but here I was really just taking the standard terminology of the field of, you know, quantum gravity that's kind of a bit remote from actual experiments, and then people just call things observables that may not be.
I'm just saying that because there is a counter, well, let me put like that, there is a potential counter example in Yang-Mills theories where you address your gauge field and you compute, for instance, the 2-point function for these dressed fields.
Yeah.
And it violates, for instance, reflection positivity.
Okay.
So that would be, I mean, that's a terrible property. I mean, and it's a gauge invariant correlation function.
Yeah, I mean, yeah, I guess it's not just a question about gravity indeed. I think it's true in, as you say, in gauge theories more generally. No, but I think, yeah, it's a fair point that one should distinguish this. But it's just, I think, very difficult, given the formalism of gauge invariant observables, you know, to actually determine which ones of them are observables.
Thanks. Well, just as a former quantum fundamentalist, I would just make a pedantic comment that, as you said, your talk was classical. So the name refers to the hope that those gauge invariant entities will be in some form quantized, and the classical part is not easy, and there is of course no guarantee that their quantum counterparts will not have some additional horrible properties. We just hope that this is not going to happen.
Yeah, point taken.
Okay, we have a little bit less than 10 minutes left. Anyone else? Maybe someone wants to be provocational?
Renata wants to be provocational. Provocative.
No, actually, it's a very naive question to Michael. From the scattering amplitude, then usually what we do in QFD, then we construct like the cross section by integrating over angular variables and so on. And also for gravitational scattering amplitudes, you use the same flat methods or like straight space-time methods, or you take into account the fact that the background can be also curved and yeah.
So in all what I was discussing, it was assumed that it would be flat, but people have considered scattering in backgrounds like shockwave backgrounds, or I mean, an interesting background is of course like computing a two-point function in a background of another black hole. This kind of thing is interesting. Yeah.
Another non-provocative question to Michael, maybe. So when you're saying that you calculate the gravitational wave memory, or you link your calculations to the memory effect, is it then via the infrared triangle relation that you just have the soft theorems, which are basically more or less Fourier transformed version of the memory effect, or what are you referring to?
Yeah, that's pretty much how it works in practice. This is not a computation I did myself. This is work of other people.
Yeah, I'm just asking. Yeah. Okay, thanks.
So does anyone else have a question or a contribution to this discussion? Well, if that is not the case, maybe we close a little bit early, but before we all leave, let us first thank the technical staff for making this possible and also letting the people online share it, and thanks again to all our 3 speakers for this afternoon session.